Dear students, in this lecture we will continue our previous topic in which we have discussed the motion of a fluid in the presence of a cylinder when your cylinder was moving rectilinearly in positive x direction. So now we are considering another case in which this is the same topic, fluid motion in the presence of a cylinder, and cylinder is circular, presence of a circular cylinder. So we are considering case 2. What is our case 2? In case 2 we are assuming that cylinder is at rest and fluid is moving rectilinearly. Now this is a very interesting situation. What happens in this situation? Suppose I say that initially I am taking the case 1, first situation. Suppose your cylinder is moving. Cylinder is moving rectilinearly. In x direction, rather in positive x direction, okay, which we discussed in the previous lecture. That means this is your cylinder and your cylinder is moving rectilinearly in positive x direction. This is the first situation. And then second situation arises that the fluid which was at rest, when the cylinder was at rest, the fluid starts to move in negative x direction with the same velocity u. So in second situation, fluid starts to move in negative x direction with the same velocity. So what will happen, as it is the same velocity, the cylinder will come to rest and the fluid will start moving. So we will reach to this situation. It simply means that to attain this situation, in first situation we will move our cylinder with velocity u in positive x direction, and in second situation we start the fluid to move in opposite direction with the same velocity, so that the cylinder will come to rest and the fluid will start moving. So it is called the fluid streaming in the presence of a fixed cylinder. You can say this case 2 may be mentioned in another way. I may say this to be fluid streaming. Fluid is streaming in the presence of a fixed cylinder. In the presence of a fixed cylinder. We may also say the situation in this way, fixed cylinder. Now for the first situation, what will be your W? As I did in the first article, your W1. This situation is W for the complex potential. For first this situation, your complex potential is W. For this situation, suppose your complex potential is W1, and for second situation your complex potential is W2. So what is your W1? You have calculated it earlier. It is UA square upon Z. So it is for first situation. Now for second situation. What happened in the second situation? your fluid starts to move in negative x direction. So what will be your x component of velocity? U will be minus u. This is second situation. This means minus delta phi delta x will be minus u, or integrating phi will be ux. Now delta phi delta x is equal to delta psi delta y, and the value of delta phi delta x from here it will be u. So integrating psi is equal to uy. Now what is w in this case? W2 is equal to phi plus I psi. Phi is ux and psi is uy. So solving it becomes uz. So it is w2. Now in our case it is the combination of this type of situation and this type of situation. This is the second situation. So combining the two, what is finally Rw? W is equal to ua square upon z plus uz. This is your W. And we will discuss our streamlines, potential lines, velocities, stagnation points, etc. for this situation. I have my W as ua square upon z plus uz. You may write it either in x and y, or you may write it in r and theta as you wish. So first of all, I am taking W to be phi plus I psi. It is ua square upon r cos theta minus I sin theta plus ur cos theta plus I sin theta. You may separate real and imaginary parts. Cos theta upon r plus ur cos theta plus I ur sin theta, this one, minus this one, ua square upon r sin theta. So comparing, you may get phi is equal to ua square upon r plus ur cos theta. And what is psi? U minus ua square upon r. This is ur. ur sin theta. So these are phi and psi. Many times it is written that phi may be taken as a upon r plus br cos theta, and you can calculate a and b according to your boundary conditions. So by putting phi to be constant, you may get potential lines, which you may calculate potential lines. In this case, your potential lines will not be the visible lines, or you cannot get the idea from the mathematical expressions. So we will bother about the stagnation points, and psi is equal to constant will provide you the streamlines. So you can solve these yourself. Now we come to what will be the stagnation point, or what will be the maximum velocity. So for velocity, we find what is dw dz. We have w is equal to uz plus ua square upon z. ua square upon z. which may be solved to u may be taken outside, or you write u z is r cos theta plus r I sin theta plus u a square upon r cos theta minus I sin theta. Since I am interested in dwdz, so first of all I'll write it as u minus u a square upon z square, and which may be written as u minus u a square upon r square cos 2 theta, and then I'll have minus with minus symbol, so plus I u a square upon r square sin theta. This is our dwdz. So I'll put modulus, it will be modulus of this, it will be modulus of this, and if I calculate it at r is equal to a, I'll put a here, I'll put a here, so it will be simply modulus of u 1 minus u is common, 1 minus cos 2 theta plus I sin 2 theta. This is 2 theta, not theta. Sin 2 theta. Sin 2 theta. You can calculate it easily and you will get twice modulus of u sin theta. Now this is your velocity. This is the resultant velocity. So from here you can see that what is the stagnation point. What happens at the stagnation point? dw dz is 0 at stagnation point. I'll write on the next page. Your dw dz means your q comes out to be twice u sin theta. Okay. Now for stagnation point q should be 0. This implies sin theta is 0. So what is the value of theta? 0 and pi. And what is your maximum velocity? Because the maximum value of sin theta is 1, so your maximum velocity is twice of u. Now you see how will I calculate it? How will I draw the stagnation points? This is your cylinder. Cylinder is at rest and your fluid is moving in this way. Okay. Now theta is equal to 0 is this line. This is your theta is equal to 0. Theta is equal to 0, and this line is for theta is equal to pi. So these are the 2 points which are the stagnation points for the streamlines. So this line is called the stagnation streamline. This is the stagnation or streamline corresponding to stagnation point. Similarly, this line is stagnation streamline. Now your fluid is flowing in this way. So what will be the flow pattern? The fluid comes in this way. It will go around the circle because circle is fixed, cylinder is fixed. So this is the direction. It will move parallelly. So this is the flow pattern. Likewise in this direction it will go like this. So these are the flow lines. You see that the flow pattern is symmetrical. So the important thing is, or the physical interpretation is, that flow is symmetrical about x-axis. So this is one characteristic of this flow. And now we will calculate what is the pressure, as we calculated in the previous article. So now we calculate the pressure. For this, again we know that pressure is defined as P plus half rho Q square is equal to constant. In this case, because fluid is flowing, we cannot assume that it is at rest at infinity. Rather, we will assume that it will be at constant velocity at infinity also. That simply means that at infinity, that means at r is equal to infinity, let P be pi and Q be u. So putting it here, we will get what is the value of constant. So constant is equal to, in place of P I'll put pi, and in place of Q I'll put u. So it is the value of the constant, and putting this value, I'll get from B P plus half rho Q square is equal to pi plus half rho u square. Now I will put the value of Q square, and solving I'll get P is equal to pi plus half rho u square minus Q square. You have calculated Q square. Solving you will get pi plus rho u square by 2 1 minus 4 sine square theta. You can put the value of Q square and will get this one. Now this is the pressure. Pressure at any point on the surface of the cylinder. Now suppose we want to find that what should be the pressure or what should be the velocity to prevent the cavitation. So as I told you earlier, that in order to prevent the cavitation, the pressure should be positive. It simply means that there should be a contact at this point of the fluid and of the cylinder. If pressure is negative, it simply means there will be a gap. There will be a lack of contact between the fluid and the cylinder, and cavitation will start. So to prevent cavitation, this should be greater than 0. This should be greater than 0 to prevent cavitation. Therefore, solving it, you will get pi plus rho u square upon 2 1 minus 4 sine square theta greater than 0. Now we see the behavior of pressure at the stagnation points, because those are the points where the velocity comes to be 0. So at the stagnation point, theta was 0 or theta was pi. So at theta is equal to 0, this gives pi plus rho u square upon 2, which is already positive. Okay, so there is no chance of cavitation at theta is equal to 0 point. Now to find the condition at theta is equal to pi, at theta is equal to pi, we had our stagnation points at 0 and pi. At theta is equal to pi again, you get sine pi to be 0, you get pi plus rho u square by 2, which is again positive. Now we see what will happen at theta is equal to pi by 2. At theta is equal to pi by 2, if you put here, you will get pi plus rho u square upon 2, 1 minus 4. And it should be greater than 0 to prevent cavitation. That is pi minus 3 rho u square by 2 should be greater than 0, or u square should be less than twice pi upon thrice rho. So it is the condition that if u square is greater than 2 pi by 3 rho, the cavitation will occur. Similarly, you can calculate the kinetic energy as we calculated in the previous article. Kinetic energy is minus rho by 2 phi delta and ds. Perhaps I missed this minus symbol there, so you put this minus symbol there. This is minus rho by 2 phi delta r, because delta phi delta n means the normal component of velocity, which is the same as the radial component of velocity, and a d theta, where theta will go from 0 to 2 pi. So now you put these values and get this value of kinetic energy. So this is all about this second type of situation, when your fluid is streaming but cylinder is at rest. Thank you.